My name is Tyler Ray, and I'm a postdoctoral researcher in John Rogers Laboratory in the Center for Biointegrated Electronics in the Simpson Query Institute for Bionanotechnology here at Northwestern University. My research, along with several of my colleagues, focuses on developing a small, thin, soft, epidermal microfluidic device platform for the collection and analysis of sweat, an example of which is seen here as it fills with artificial sweat. Now, sweat is an interesting and important biofluid that offers a non-invasive window into the health and physiological status of an individual. Current sweat collection methods are limited by the coupling of a hard and rigid device, much like a watch, to the skin, which requires either an external strap or tape to maintain contact with the skin. Working with our theoretical modeling collaborators in the WAN group and the mechanical engineering department here at Northwestern, we've designed a device platform, as seen here, that harnesses the power of soft mechanics to integrate intimately with the skin and capture sweat directly as it's produced by the eccrine sweat glands. We use the sweat glands as pressure pumps to route the sweat throughout the device in embedded microfluidic channels. This type of intimate interface between the skin and the device enables new measurement capabilities not possible with current methods of sweat collection. With these epidermal microfluidic devices, we can take a variety of important physiological measurements. When worn, sweat enters the device from these 5 inlets and then is transported either to this outer serpentine channel seen in blue or these colored spots at the center of the device. Now, this skin-like microfluidic system can, for the first time, record an individual sweat rate during exercise. Now, we achieve this by observing how much sweat enters the device, specifically in this serpentine channel, and we observe this filling behavior and record the volume by looking at how this channel turns from blue to clear during a fixed period of time. Each one of these colored reservoirs provides information about particular biomarkers present in sweat that are important for assessing one's health state. With this device, we are specifically detecting levels of pH, which is an index of hydration state. We're recording chloride levels, which is a measurement of the electrolytes present in sweat. We're also looking at the glucose levels in sweat, which is the amount of sugar in your sweat. And then we're recording the lactate levels in sweat, which is a measurement of the exertion levels during exercise. The concentration of each one of these biomarkers is a key piece of information that's important in understanding the health and well-being of an individual. Detecting the concentrations of these biomarkers typically requires external laboratory analyses. We're actually able to achieve this on the device because each one of these colored reservoirs contains a specific colorimetric dye that we've developed to react with and change color in response to a particular biomarker. Now, these color changes that we'll observe, for the pH, it will be from yellow to green. For chloride, we'll observe shades of blue, so a pale blue all the way to a dark blue. For the glucose reservoir, we'll observe a pale yellow to a dark brown. And for the lactate, we'll observe a pale yellow to the green. And each one is arranged from either low to high concentrations of these biomarkers. Now, these color changes allow us to measure the precise concentration of each biomarker, and we're able to achieve an accurate quantitative readout via the camera in a smartphone. Now, this robust platform for the analysis of sweat will have specific applications that we can develop in conjunction with collaborators. Specifically, we're working with the Northwestern University Feinberg School of Medicine to identify some of these applications. In particular, we're able to have devices that are for clinical applications, where we're working with Lurie's Children's Hospital in downtown Chicago to design a device that improves the efficacy of the cystic fibrosis diagnostics in young children. We're also working with the NCAA teams here for sports-based applications where we want to monitor the performance of athletes during exercise. We also have devices that are for personal applications or more for at-home applications. In this case, we've designed them in conjunction with the National Kidney Foundation to monitor a person's hydration state in order to raise awareness for the importance of hydration for kidney health. Now, each one of these devices can provide real-time quantitative information to the individual that is readily understood and visually clear. Now, these devices They're about the size of a quarter and the thickness of a quarter, and they are disposable, easy to use, and provide this real-time individual feedback for a diverse range of applications. My name is Tyler Ray, and this is just one of the many exciting projects that we're working on in the Rogers Group as part of the Center for Biointegrated Electronics here at SQI.